Hello, everybody. I'm sorry for being a little late. I've got a physical at 11 o'clock, and so my timing got all messed up. Can everybody hear me? Can everybody hear me there?
Yes.
Okay, wonderful. Thank you. Okay. Now, types of reactions. Okay. Okay, I'm going to switch. Yes. I might. I just said I might. I don't know how far I'll get today. That's what I was. That's the preface of what I was saying. Okay. I might do it to Tuesday, but I hope not. Okay. Because if I shift it to Tuesday, then it messes up everything. Regarding the classroom and other things, because other people are using the classrooms. Okay, can everybody see the PowerPoint now? Okay, I introduced you to oxidation reduction reactions, and what we're now going to do is go through combination reactions first, types of oxidation reduction reactions, combination, and the other word I used for that before in my thing was synthesis reaction. So essentially, when you have a combination reaction, it's like A plus B goes to AB. And an example of that would be hydrogen plus oxygen goes to water. Very straightforward one, okay? And then you balance it. So that's a combination reaction. It's also called a synthesis reaction. So you have synthesis is the other name, and it all depends on the book you're dealing with, okay? So A plus B goes to C. I just like the AB goes to A plus B goes to AB instead of having it be a C. That's just my preference. So here's an example. Aluminum plus bromine goes to aluminum bromide. And basically it just kind of breaks down with the different examples. And basically the oxidation numbers change for each. When you start, notice the oxidation number for the aluminum is 0, as is the bromine. The aluminum goes to +3 because remember where it is on the periodic table. It's below the boron, which is +3 based on what I gave you before. Now, what I recommend when I give you the exam on Monday, as well as the periodic table you have, is write +1, +2, +3 across, and then do the -1, -2, etc. the other way. Yes? Aluminum, also boron and gallium going down the list. It could be +3, or in the case of indium, it could be +1, I think, but I'm not exactly sure. But basically, boron, aluminum, and gallium could be +3. But in this case, it's aluminum, okay? And aluminum, the only one is +3, yes. Well, they could be +1 all the way up to +7, but they're normally +1 or 2. And we'll get into that in the next chapter, in the next 2 chapters, how that works. Because it all has to do with the outer shell electrons, and that's coming, okay? So basically the bromine is -1. The decomposition reaction is the other way. So essentially that is AB goes to A plus B, going the other way. And an example of that would be lead sulfide goes to lead plus sulfur. Okay, so there's a whole variety of different examples of those kind of things. Yes.
Going back to the example of aluminum, would that compound have a charge 2?
The aluminum would have +3, and the bromines are each -1, so there's 3 of them. Yeah, you have 3, -1 for each one. Yes.
Do you want those charges to always balance out?
To be zero, yeah. They're all zero. That's the whole point. Unless you have an ion that might be -1, -2, whatever. Okay. And that's like this one here. Potassium chloride goes to potassium chloride plus oxygen. So chlorate goes to oxygen from that. Yes.
Then why does the aluminum say the charge is 0 if it should be 3? In reality,
Well, it starts at 0 because that's the aluminum metal. Because it's in a solid form, it's all the extra electrons are going around, and it's just defined as 0, and that'll be explained later. It only loses electrons when it goes to form an ion. But in the metal form, the solid metal form, it's always 0. That's just by definition.
okay.
Because you're comparing charges between one and the other. But aluminum conducts electricity, so there's plenty extra aluminums, and you'll understand that again. And I appreciate your asking, but you're kind of going ahead of 5 and 6 here, that we're going to cover that. But right now, I need to wait until I get to that part, okay?
Okay, that's fine. But because the product side, it says aluminum is still +3, but there's 2 aluminums, would it be +6?
No, because there's 2 aluminums and each one is +3. So if I go ahead, I'll put some stuff from the 5 or 6. This is what aluminum looks like with 3 extra electrons around it in the outer shell, okay?
Yeah.
When you lose them, it goes to aluminum +3 with no extra electrons in the outer shell. That's discussed in chapter 5 and 6. But right now, we're just talking about oxidation numbers, and that's how it's defined. But it'll become clear when I get to that in the chapter.
We're going to be tested on.
No, you're going to be tested on the things of making up that. That's why you have the periodic table with you, +1, +2, +3, when they form ions. When they form compounds, they go to that form. You're not really given the explanation yet. I just want you to know it's +3. And oxygen is always -2. Okay? It's just a matter of, right now, you don't know why. Take my word for it. There's a reason, but it's all about putting pieces together. It's like we're painting a picture here. And it's not going to become clear until you see more of the context, okay? So anyone else have a question? They're good questions. Okay, yes. You had a question?
No.
Paige, did you understand what I was saying? No?
I think he's asking a different question, but I think the 2 implies the plus aluminum and bromine, so it cancels out.
No, there's 2 aluminums, which is +3 for each of them. And the bromines together, yeah, you have 3 bromines with each one. So you have the +3 and then 3 -1s for the bromine. And that has to do with the nature of the bond, because essentially it goes like this. It forms a bond there with this one being negative, 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 and this is +3. So they're all attached together. But that's in 5 and 6.
No, I understand that. There's the 2 aluminums, and then it would be 6 bromines, because you have the 2 as a coefficient before the compound.
Right, it's just the way the compound is listed. Because it's a solid in that form, it looks like that, the powder. Because it's a solid, it'll essentially be, or a gas, it could be a gas, I don't remember. But the point is, or liquid, the point is, that's the molecule, aluminum bromide, and there just happens to be 2 moles of it. Okay?
So the 2 also applies to the bromine.
There's 3 bromines already, so there'll be a total of 6 bromines, yes. Okay? So that goes, everything in the front goes all the way to the back, just like in the other ones. Just like here with the 2 in front of this is 3 oxygens attached to it. And again, it forms an ion, and that'll become clear in chapter 5 and 6. But I appreciate your thinking ahead of where we're going with this, but it's a little early. I can't go forward and then back to this now. I'm just asking you to trust me, okay?
I just didn't understand how the analysis.
Well, yeah, but right now I'll just take it, ask it, because the definition is about oxidation numbers. That's what you start with, and then you're essentially, you're explaining them a little later, okay? Okay, so basically you have there, the chlorine is +5, and someone asked about chlorine being +5. It could be all the way up to +7, and that'll be explained later. the chlorine could be +5, it could be +7 also, as well as the other ones. Just like, for example, if you have KCl, it's -1. If you have KClO, it's this is -1. This one becomes then +1, and then you have KClO2. This is then +3, and then KClO3. This is +5, and then KClO4, which is +7. So there's a whole variety of different oxidation numbers for chlorine, but you'll just get the hang of it. And I kind of addressed that in the when we talked about perchlorate and chlorate and everything in the naming. So it all fits together. So we're kind of going from different angles at it, okay? Does that make sense now to you? You look a little baffled in your eyes. You get it? Okay. Oh, all right, well, you will. Okay, so just do the reading, whatever, it'll come clear, okay? I'm trying to do a little bit of interpretation. Now, the next one's called a combustion reaction, and this is a special kind of thing. And essentially, it's like this: you have carbon plus oxygen goes to CO2, and that is essentially A plus B goes to AB. Also, but a combustion reaction is when you got it reacting with oxygen. And in a way, I don't know why he just doesn't put AO2 there. That's what I would do on it, and the different variations of that. But combustion reactions are all about burning something. Sulfur plus oxygen goes to SO2, and the sulfur starts at 0. The oxygen's there, 0 also. The sulfur goes to +2. Each one of these is -2, and there are 2 of them. So then the whole thing ends up being 0 there. And that'll become clear also when we get to it. Okay. Yeah, oxygen will always be involved in a combustion reaction. It's burning, just like fire. Yeah.
How would you get a charge of +4 for sulfur with the ionization?
Because 2 of the electrons from sulfur go to the oxygen to be shared with the oxygen, and so it gets what's called a formal charge, and that's going to be discussed in chapter 6 or 7. No. The kinds of reactions will be, and the oxidation numbers, not the explanations for them at this point.
Right, but we don't know how to do the oxidation.
Well, yeah, you just +1, +2, oxygen's always -2, etc. There's a chart in the previous thing with all the oxidation numbers.
Oh, so if you started with oxygen, you would know that there's charge negative.
Right.
There, so the other one has to.
Right, so that's basically use oxygen to decide it. And it's about putting the pieces together. And that's why you let you use that periodic table and say right on the top, just like that, and then you'll get the hang of it. But I'm asking you to reserve the explanation for why it is the way it is until we get later in the semester. And I think it's cool the fact you're thinking ahead. Yes.
But then there's the fact that like with chlorine, it's supposed to just be -1, but it's
Right.
just +5.
But when it's part of an ion, it can lose electrons and go all the way up to +7, and that's discussed in chapter 6. And
So
you'll
we don't need to know that for this.
no, because that's losing outer electrons. So they're called valence electrons that are involved in bonding, and basically that's what's happening with that. And so basically you get what's called the formal charge, and that's the oxidation number. But unfortunately, that's a little later. And right now, I'm painting a picture, leaving out some of the things. How many have ever painted by numbers? Well, if you paint by numbers, often there are blanks in them as you're putting in the different colors. I did it when I was a kid years ago. And yes,
All right, so on our quiz, we had a question that said, Mary Smith made magnesium oxide in the laboratory by burning pure magnesium and oxygen.
right.
So is oxygen always deoxide? Because you said.
Yeah, burning and magnesium oxide. Yeah, it's just this magnesium plus oxygen goes to MgO. Because I even put in later part of the quiz what the formula for magnesium oxide was. Oh, shoot.
I was just wondering, so combustion always has like, it's the oxide,
Right,
basically.
right. You're forming the oxide. And basically the whole concept of oxidation, oxidation can involve other things, but combustion specifically refers to oxygen burning something, okay? Like you can burn magnesium things, okay? And basically it goes up to +2 with a -2 associated with this. Displacement reactions here, and this is called a single displacement, single and double, okay? And an example of that would be reacting of strontium with water to form strontium oxide, or sodium plus water goes to form sodium hydroxide. That's the other possibility there, plus hydrogen. Okay, and then you balance that one too. Okay, so there's a whole variety of different things related to what these are. Hydrogen displacement in this example is one. And there's another one related to this too, where you've got titanium chloride plus magnesium goes to titanium plus magnesium, and metal displacement. And again, you got the changing in oxidation numbers, and then the halogens replacing each other there, and they're all oxidation things. And this is the activity series for metals, and it kind of illustrates how these work, okay? So hydrogen there, displacement there, and I do not ask my students in Gen Chem 1 to learn this chart or activity series, because that comes into electrochemistry later in general chemistry too. But it's just an interesting aspect of looking at it for those that this is helpful, okay? Okay, the activity series for halogens. Halogen displacement is a bunch of different examples, and that has to do with ability to them to oxidize each other. And then types of oxidation reduction, disproportionation. The same element is simultaneously oxidized or reduced. And here you can get chlorine reacting with hydroxide to form hypochlorite and chlorine. And an example of that would be with sodium hydroxide. That's to essentially make sodium hypochlorite plus sodium chloride. And that's what's an active bleach solution that you buy from the grocery store. If you look at the thing, it says sodium hypochlorite on the side, and that's essentially putting sodium hydroxide solution and then bubbling chlorine gas through it. And that's how they make bleach. Okay, so that's called a disproportionation reaction. Okay, and basically there. Now classify each of the possibilities there. Let's classify them. What is the first one there? This is to form a solid. That's a precipitation reaction, precipitation reaction, precipitation, okay? And it's also a combination reaction, okay? And then you've got the other ones related to this. This would be a neutralization reaction here. And this is a single displacement, single, and then this is a synthesis reaction. So that's essentially how we put the pieces together. Yes? Well, that's the beginning of chapter 4. If you like, I could go back to that slide when I'm done these. I'll just go back and refresh that. I've only got 11 more. Okay, I just want to finish it. Any questions? Other questions? Okay. What? Precipitation reaction, yes. Okay, sorry. My handwriting's bad, but I think the next slide says, there it is. Okay, see? Acid base. I'll just delete my thing, it messes it up. Okay, and then redox hydrogen displacement, and I prefer to have it be a single replacement reaction, and this is a combination reaction or a synthesis one. chemistry breathalyzer, and that's interesting, but not very useful. Now, the concentration stoichiometry is the next part, but before I go to that, you had the question about that. So let's go back. Let's go back to the previous slides. Okay. Okay, this is precipitation reactions. And again, this is double displacement, as I said before.
So precipitation, double displacement are the same thing.
Yes. Okay. Neutralization is the other one, and I'm going to talk about that at the end. But yes. And so here, these are the things here. AB plus CD goes to AD plus CB, and that's a precipitation reaction. So essentially, you got the molecular one, then the ionic, and then the net ionic, and that's that. That's the precipitation reaction. Did that answer your question?
Yes, I was just wondering, I didn't know if they were like a subcategory.
Well, they are kind of. These all kind of interact with the thing. The neutralization, and that's what the last part of the chapter is about. After we get into molarity, that's what I'm going to talk about last for this chapter, okay? And that's what I also talk about in the lecture. Now, those of you who already saw my lecture with the thing, with the acids and bases for the lab, did you understand what I was doing with that? Those that already had the lab with me? Okay, so basically this will become clearer as we get to it also, okay? Again, what I'll try and do today is I'll do it on the thing here and do a little video of it. I can do a video of it so you can watch it. But unfortunately, I like to wander on the board with it, but I can use the thing. I can use that to make it easier if you want. But are you sure you can't come tomorrow at 1:30?
I was supposed to have a study group from 12 to my bio.
Oh, okay, I see. Okay, so let me just put up the video for you then. We'll do it that way, and I'll just use the screen. Okay? Okay, yes.
So for the test, we're gonna just like be expected to know, like to classify what kind of reaction it is, and then the oxidation numbers on there.
What? Sorry?
So for the test, we're gonna have to just be able to like recognize what kind of reaction it is, or we're gonna have to like write.
Well, some, yeah, but mainly they'll be asked like reacting iron with the problems I gave you, iron with oxygen to make iron oxide,
Okay.
or something, or the aluminum one, just like in the quiz.
Okay.
You're not going to see any surprises. Okay, it's all related to that. So I'm going to go back to the original place in the slides.
What was the neutralization reaction?
We're getting to that.
Okay.
Yeah, that's down later. I just got to move down to the next part. Just a moment. Yes, question.
The precipitation is when you react into aqueous and then you get a
A
solid.
solid, correct. Okay, I'm going to share the screen again with you folks. Sorry, I'm going back to the slides now. Okay, a breathalyzer, basically, it reacts with the alcohol in someone's breath and then forms that. And then there's a sensor that registers how much is in there with a photocell and the filter. So it just registers the color. Now, solution stoichiometry, and this matters with all of these factors, it has to do with the concentration of the material converted to moles per liter. So essentially what we start off with is moles of solute per liter of solution. Now, if you remember the chart, and I addressed this a little bit in the lecture for the things, if you remember the chart regarding this, you're going here grams to moles of reactant to moles, and back to grams again, if you remember from chapter 3, okay? When you have a solution, it would be in moles of solute per liter, because you can't easily, when you have a solution, you can't put it on a scale and have the scale say, oh, it has this amount of material in it as well as this amount of water. It doesn't work that way. So basically, you weigh a certain amount of grams into it to make the solution. You mix it with water. That gives you the solution, which it may be 1 molar. So then you'd say take a certain amount, like 50 milliliters of material. Then you know exactly how many moles of material you put in there. So it's like a replacement for the grams that you would measure on a scale to get the substances to react. And so in this case, it's all about molarity. Okay, what mass of Ki is required to make a 500 milliliter thing of 2.8 molarity Ki solution? And this works with acids and bases too, which we'll talk about. So you start with the volume of the Ki solution, okay, and then go to moles, okay? So you have the moles related to it. You start off with 500 mils, okay? And you convert that to liters. That's the first step. You then have that you want a 2.8 molar solution. So you have 2.8 there. What cancels? The milliliters cancel here, and then the liters of solution cancel here. So now you've got the amount of moles of Ki that goes in there. You then convert it to grams. So basically, you would take 232 grams, and then you add it to 500 milliliters of water. That's how you make the solution. Okay, and what you're going to be doing in the lab, and some of you already had the lab, is essentially the sodium hydroxide has been made into a 0.25 molar sodium hydroxide solution. And in the vinegar is at 6%. And you're going to figure out what the molarity of the vinegar is that you're going to be doing in the lab, okay? And it really works pretty well. So basically, these all convert to this going across, and you have got moles, and now you have grams. So preparing the solution, you add the solid to it, you then add up to the marker, and then make it. Dilution is a process to make a less concentrated solution, and you have moles of solute before equals the moles of solute after. The only thing you've done is add more liquid. So that's essentially what you're going to do with the vinegar. You take 10 milliliters of vinegar, you add 50 milliliters of water to it, 10 milliliters of vinegar, you add 50 milliliters of water. Does that change the amount of vinegar in the solution? No. All it does is separate them and make them further apart. Okay, so essentially the moles on each side are the same. So the moles of the solute is the same as the moles on the other side. So that works for a dilution experiment as well. So basically those are the kind of math there. So here you plug these values in there, and I'd highly recommend you look at the problems related to that in the chapter also. And basically you plug the values in there, you just don't know what the other one is. You set up the equation and just plug the numbers in. This is what I've had chemistry students have the most easy with, because it's just a matter of plugging the numbers in the right place. And this is how you're going to be doing it with the acids and bases also. Yes, did you have a question? Okay. I got to pay attention to the eyes here a little. Okay, now dilute 3 milliliters acid to make a total volume of 60 milliliters there with water, and basically that. Gravimetric analysis is another part of this to find out how much of precipitate you have, and that is a thing too. Now titrations, this is what the acid and bases thing, this is what you're going to be doing also with this. And the titration aspect of this has to do with how these things work together. So essentially the titration part you have the equivalence point, because essentially what you're doing with the lab is you're taking CH3COOH, which is the acid, you're reacting it with sodium hydroxide. The result is to get sodium acetate, which looks like this, plus water molecule, okay? And the equivalence point is where the reaction is complete. And I go to this more depth in the pre-lab lecture, okay? So how many have the lab this afternoon? And how many on Friday? Did you folks had it on Tuesday or Wednesday, right? Okay, so good, okay. So basically this is covered in my other part, but we've only got like 4 slides left, so it's so basically I'm just kind of redoing it. And this is essentially what you're doing, where you have the vinegar in here, the vinegar and the water, and it goes to form the pink. So essentially you have it like that, okay? Titrations can be used analysis of acid-base reactions like this, and then you have the other things related to each of those. Redox reactions, this is a titration reaction, and you base it on the color change. And this is a lab that is done at some colleges and universities with a titration, usually in general chemistry too. But it's quite a cool experiment to do a redox reaction as well. Okay, now what volume of 1.4 molar sodium hydroxide solution is required to titrate 25 milliliters of this? So before I do that, what I want to do now is introduce the whole concept of it. I'm going to go out of the slides for a second and bring in part of what I was doing before. I'm going to add some slides just so we can go where to do this with this here. And I'm going to go relatively quickly through this because this will serve as a reminder for some of you what I cover in the lab, but it's also a useful thing also for those too. So now what I'm going to do now is essentially define the acids aspect to it. An acid is essentially a proton donor with the Bronsted-Lowry definition, or the Arrhenius one, it is when it's dissolved in water, it gives hydrogen ion. Okay, a base is defined as a proton acceptor. Okay, and when dissolved in water, it gives hydroxide ion. Okay, so essentially it's usually in this form: HCl aqueous plus sodium hydroxide aqueous, okay, goes to salt, a salt aqueous plus water. Okay, that's the molecular equation. This is the molecular equation for it. Okay, the ionic one is you break it all down into pieces: H plus Cl minus plus sodium plus OH minus goes to form sodium plus chlorine plus water. And essentially the things that are common to both sides of the sodium and the chlorine, they're both there. So you have the net ionic equation, which is this: H plus OH minus goes to form a water molecule. Okay, and that's in the form of a liquid. This is aqueous and this is aqueous. So that's the definition of an acid and a base. And if you notice, this is a one-to-one relationship. So what they said about the equivalence point on the previous slide, when you have the titration there, the equivalence point where the reaction is complete, that's where you have the hydrogen, the ion plus a hydroxide ion, goes to form the water molecule, okay? So that is the nature of an acid-base reaction, okay? And then you have those things there. So essentially that goes to get the titration. The acid-base reactions there, where you react sodium hydroxide with sulfuric acid to form water and sodium sulfate, or in the case of yours, you've got vinegar with this, and it makes sodium acetate, which looks like that. Okay, so basically they're different kinds, and then there's the acid-base part. Okay, so yes. What? In the slides, it's going to be in the Chang thing, and I'm going to save it in the Chang folder. I'm also going to go to the other one for yours too, but it's not the same. Okay, so what volume of a 1.4 molar sodium hydroxide solution is required to titrate 25 milliliters of this? So essentially, you write the chemical equation first. So what's the chemical equation going to be? Well, you put the sulfuric acid plus the sodium hydroxide goes to form sodium sulfate plus water. And it has to be balanced. So this would be a 2 in front, and now it's balanced on both sides. So now you would have a 2 associated with that. So you write it down first there, and you balance it. Okay, the volume of acid equals the moles of the reactants. The moles equals moles. So the equivalence point is equal. That's where it turns pink. That's the equivalent point. Okay, and I'll address that a little bit more in those of you who didn't see the other lecture. Okay, so essentially you start off by taking 25 milliliters of this. And how many milliliters of the vinegar did you use? Huh? 10 milliliters of vinegar. And you didn't know what the molarity of the vinegar was. The molarity of the vinegar, you don't know that. That's what you don't know. Okay, so basically you didn't know what that was there. The sodium hydroxide then is 2 for each of these, and you add the sodium hydroxide for that. So you have the moles of sodium hydroxide there. And again, you then convert it to molarity of the sodium hydroxide. What was the molarity of the sodium hydroxide? 0.25. So this is moles per liter going the other way. So this would essentially be 0.25 molar sodium hydroxide. And essentially it shows you how to do that in the experiment that you did.
What is SOLN?
That's the solution. Milliliters of the solution. And you get 158 milliliters if you're going to calculate that when you calculate it. But you did it, you'll do it experimentally in the lab, or you did do it experimentally. And you did get that part in your lab, right? Okay. So basically the experimental part. So basically the oxidation thing for this, is done the same way, and basically it's volume to moles there go to form there related to it, and then you get to the last part of this. Okay, so you can do it the same way. I put an X through it because this is better covered in electrochemistry. Okay, chemistry in action, metals from the sea. Okay, that finishes the slides to this. Now what I'm going to do is go over in your book just to see what is covered with that in the book there. Hold on a minute. And just be with me. I just want to go for 2 minutes in this just to refresh what we did before. Here, the acids and bases, and essentially I put down the definitions of acid. I'll get more into that in the thing this afternoon. But basically, these essentially go with the different kinds of acids, the neutralization reactions, net ionic there, use the solubility rules there. Solution stoichiometry, I addressed that better in the slides. But again, he doesn't use any transitions, which is really annoying. I like the transitions, so I encourage you to use those too. The titration aspect, that's covered also. And then oxidation reduction reactions there. There, rusting of iron, oxidation reduction, going from one to the other. Rules for assigning oxidation numbers, and we kind of did that already with the -2, putting the pieces together, and then identifying them related to what the different ones are of that, and then the activity series of the elements, and then redox titrations. That's the last of those slides. So essentially, because these slides don't have any of that, and what I'm going to do next Monday is essentially, we've covered the stuff for chapter 4, but I'm going to teach you another thing about balancing oxidation reduction reactions, and that'll be on the next exam, not on this one coming up on Tuesday. Yes?
So we will have our exam on Tuesday.
No, it'll be on Monday. I'll have new material of balancing oxidation reduction reactions on Monday, but it will not be on the exam.
Okay.
So basically, I'm going to add some more material to chapter 4 that I like, that's very good to understand balancing equations, and we'll use it before we get into that. But that's not going to be the exam. Everything I covered today is going to be on the exam.
So you were saying how you were considering putting it on Tuesday?
No, I'm not.
Oh,
No, I covered what I needed to in the chapter. Because I was uncertain as to how much of Chang was covered in our textbook. And I didn't know until I said the slides. Yes.
So it's chapter 3 and 4 in the like physical copy, textbook copy?
Yes. Chapter 3 and 4 of the physical talks. And
The PDF version on Google.
for Hein, there's a PDF with that there. And I think I have a PDF of another textbook in there too. You can look at.
You know what the chapters are for that one?
No, you'll just have to look and see where they are, the different sections, but that's introductory material, okay? Okay, thank you all. We're essentially done the lecture, so I'll see you all on Monday. So